In the last lecture, I had given you, last few lectures, I had given you some applications of lasers. Basically again, even in these following lectures, I will be continuing the applications of lasers. Okay. And today I will start with application of laser in spectroscopy. Okay. So, what I want to emphasize is which property of laser is used in spectroscopy. Okay. The property of monochromaticity, the property of intensity of the source, and the tunability of lasers, okay, and the resolution of measurements possible because of lasers. Okay. So, as you can see here, I have just listed out the properties used: monochromaticity, intensity of the light source. Known laser lines vary from ultraviolet to the far infrared. That means you have so many wavelengths to play around with in your spectroscopic experiments. Then you have the tunable lasers, and obviously the tuning range is very large, and then the resolution of measurement. Okay. It is not as though spectroscopy did not exist before lasers came into the picture. Spectroscopy has been there for millennia, and lasers have just kind of revolutionized spectroscopy. Okay. And that is what we are going to discuss here. Why has lasers revolutionized spectroscopy? Okay. And the use of lasers in spectroscopy cannot be underestimated at all, and should be appreciated so much from the Nobel Prizes itself, which I had discussed in my first lecture. So, you had this Nobel Prize for the frequency comb, which gives you the absolute frequency required for a spectroscopist, and then the resolution part, short pulse length, which gives you the precision in spectroscopy, and of course, the coherent source of lasers, which has an intensity much higher than the incoherent sources that have been used till lasers came into the picture. Okay. So, these are the uses of lasers in spectroscopy, okay, and it has revolutionized spectroscopy. And then if you just see some of the traditional sources of light radiation, has been tungsten halogen lamp covering the visible and the near infrared, deuterium lamps in the ultraviolet, heated silicon carbide rods, which gives you emissions in the infrared region. Then of course, the black body sources, which covers a wide bandwidth of lasers, a wide bandwidth of wavelengths. And then you have the klystron and the magnetrons, which produced narrow band microwaves. These instruments are used in your microwave ovens, by the way. And then hollow cathode lamps used in atomic absorption spectroscopy, and laser tubes, laser X-ray tubes, carbon arc lamps in the broad visible and ultraviolet. Okay. So, there were so many of these traditional sources, not that they are not used now, they are still being used. Okay. Still being used, but then many of them have been replaced by lasers, because obviously of the intensity and the monochromaticity. Many of these lines from, say, the tungsten or halogen lamp, you may not always get a monochromatic tiny full width half maximum lines from here, and then but say the hollow cathode lamp is still being used in many spectroscopic studies, because it is very difficult to place a laser there or place the laser beam into your sample. Okay. So, you have to use something like these hollow cathode lamps. Okay. So, these are not discarded fully, but the uses have become less and less as more and more lasers with wider tunability is coming into the picture. Okay. Now, why do spectroscopists need tunable lasers? So, I will emphasize in the next few lectures on the tunability of the laser. So, that is the property that I will be emphasizing on. That means this part, tunable lasers, and this part. These are the two properties that I will be making use of in the spectroscopy. Now, why? Why is it that you need these kind of tunable lasers? It's because, suppose you have some molecules or a sample, the sample that you want to study, which is a material either in molecular form or atomic form or in a vapor form, any form, you want to study that. You really want to know what are the energy levels of that system. What are the energy levels is one thing, and what is it composed of? You may have a sample which is composed of many elements or many molecules which are which have to be you need to distinguish those. Okay. So if you have this tunable laser, suppose I talk of an energy level like this for any material. Okay. It has any material, it can be electronic level, rotational level, or anything. So I need to know this difference in energy level. Okay. I need to know this difference. I need to know this. If there are some more, then I need to know this. In order to characterize my sample, or in order to characterize that material that I am trying to study. So originally spectroscopists use these traditional sources, and they illuminated with these sources the sample, and then finally checked its absorption lines or the emission lines, whatever, some lines in a spectroscopic instrument, in a monochromator or a detector which will detect any of these radiations or lines. So when I want to know these energy levels, that means I must have a source which has a wavelength commensurate with this energy level difference. Remember h nu, okay? The energy level is proportional to h nu, and the moment you say it is proportional to 1 by lambda, okay? So I need to have a source where this lambda can be tuned from lambda 1 to lambda 2 to lambda 3. And then one of those wavelengths will coincide with these levels, and once it coincides, then okay, this level exists in that sample. Or it gives an emission line, and once it gives the emission line and the wavelength it has given, exactly what is the energy level of that system. So this is what the spectroscopists want, and they want a tunable laser. See, each time they are not going to change their source. It's not that they've started with one stone, say tungsten halogen lamp. It has in the visible and the near infrared. But suppose they want something in the ultraviolet, then they have to change their source. Okay. Or suppose they want a wavelength which is close to NIR, but not exactly the one which is given by the tungsten halogen lamp. Then what do? You have to change your source completely. You have to change your complete system. So, but then if you have a source which is tunable over, say, continuously tunable over the visible to near infrared or in the UV region, then you have so many wavelengths possible from the same source. Okay. And then you study your sample. Here I have just put down why tunable lasers. They offer precise control over the wavelength of light, enabling variety of applications in spectroscopic techniques. That is what I just explained. And then selective excitation of molecules adjustable to match the absorption or the emission lines. Okay. So, I need selective excitation of the molecules. This is say one molecule. I need to selectively excite it to this level or to this level or to this level. Okay. For that, I need to change the wavelength. Okay. So, it gives selective excitation of molecules. Then high spectral resolution or narrow line widths. Okay. Here this what it means is the monochromaticity. Okay. This one, monochromatic properties of the laser. So, if it is giving just one wavelength, say only lambda 1, and it is like a delta function, that is what you are looking for. In ideal case, it is never a delta function, you will always have a width like this. Okay. So, you want this width to be smaller and smaller. Okay. So, it is a very narrow line width laser, so that you can pinpoint the exact energy level of the species. Okay. Then it can cover wide spectral ranges from ultraviolet to visible to near infrared to mid infrared region for different molecular systems. Okay. So, you should have a source, ideally a source which will travel from which you can tune from say ultraviolet to the mid infrared region, and all you have to do is change your sample. You do not have to do anything with the source, you have to change the sample and study the sample. It is not ideally possible, but okay, let us see to what extent is this possible. Okay. Then the enhanced sensitivity. Tunable lasers with its high intensity and coherence improve the signal strength and the detection limit. Okay. So, this is for systems or samples which are giving you certain emission lines or due to certain property which is very weak. One famous example is the Raman lines. Okay. In Raman spectroscopy, I will be describing Raman spectroscopy in a bit more detail, but for the moment just realize actually a Raman line or the Raman signal that is got from a sample is very weak. So, it is never detected. For a long time it wasn't getting detected. It was just the genius of Raman who could manage to do it, and Raman did it before the lasers were born. So, those are very weak lines, and those weak lines, how to make them stronger so that you are able to see with the kind of instruments that you have. That is when you use lasers again. Okay. So, that is meant by enhanced sensitivity, you know. So, you have enhanced the power, you have enhanced the intensity of the laser, simultaneously keeping the monochromaticity. Okay. And so, your signal that you get from your sample becomes stronger and stronger, and you are able to detect it. These lasers provide precision, flexibility and sensitivity critical for probing molecules or structures and their dynamics. Okay. When I say dynamics, I mean, you know, the spectroscopists want to know any process that is taking place in the sample, in what time scale is it taking place. That is when you need the short pulse lasers or pulsed lasers. You can make it shorter and shorter, as we have seen before, pulses can be made shorter and shorter. And the shortness of the pulse gives you the precision of detecting that particular phenomena that is taking place in a molecule or a system. Okay. So, these are basically the reasons why spectroscopists welcomed laser with open arms. Okay. Now, let us see what kind of lasers are used? There are many, there are many kinds of lasers available nowadays and with different wavelengths. So, but the best example is the dye laser, which can be tuned fully in the visible range. It's got a very wide spectral range in the visible region. Again, now these dyes are not all, you cannot do it from the ultraviolet completely to the mid infrared, but it's a wide range in the visible range itself. With one particular dye, you can get those wavelengths that you desire. Okay. So, the dye laser is a fantastic example to be given for tunability, okay, tunability of the laser. So, let us study what dye lasers are made of. Okay. So, generally dyes are long chained molecules, they are really long chained molecules with carbon single bond or double bond. See, I have just given an example of rhodamine 6G, which has carbon 28 carbons, hydrogen 31, nitrogen 2, oxygen 3 and chlorine. Okay. So, you can imagine there are such a big molecule, there will be so many bonds, and it is full of benzene rings, and it has these double bonds, single bonds and lots of variations, and all of them are in this molecule. So, there are lots and lots of possibilities. Now, so because there are lots and lots of possibilities of how these molecules vibrate or how these molecule exchange energy within itself, gives rise to all these energy bands. Okay. The ones I have shown in red are energy bands, the ones shown in purple are also energy band. The ones shown in red are electronic energy levels. Okay. And the ones shown in deep blue or violet, they are rotational and vibrational levels together. Okay. So, the moment I say it is an electronic level, that means the energy difference between these two electronic level will be in the visible ultraviolet of that kind, because they are wide energy levels. They are separated by a large energy gap. Okay. So, these are all electronic levels. Now, where do these electronic levels come from? The electronic level comes from the electrons which are hovering around this molecule. You have all these bond structures and there are so many electrons over there. And the energy levels of those electrons give rise to these energy levels here. So, this is called S1, this is called S0, this is S1, this is at S2. These are called the singlet levels. Singlet levels mean that there are the electronic structure has the two electrons, the last two electrons in this whole structure, they have opposite spins or they have antiparallel spins. So, S becomes 0. The spin quantum number becomes 0. Okay. Since the spin quantum number is 0, what you get is S equal to, there will be just one state because of this spin, which are antiparallel with each other. Okay. Details of that, if you can read up some books, you will know. I will not go into the details of that. Just understand that these are electronic levels is given rise because of the antiparallel spins of two electrons, okay, in some of these orbitals here. Similarly, the triplet state is given rise because the two spins of the electron are parallel to each other. Okay. So, if they are parallel, S becomes This is small s, not the capital S here. S becomes 1. So, ms can take the values -1, 0 and +1. Try to recollect some of your spectroscopic studies which you may have done sometime. Okay. So, if spin is 1 of the electrons, then these are the 3 possible states. So, there are triplet states which gives rise to these triplet levels, okay, T1 and T2. Okay. These are the triplet states. Now, what about these levels here? These levels are the rotational and the vibrational levels. So, that means the bonds between carbon and hydrogen, or between carbon, nitrogen, or hydrogen and nitrogen, there are so many bonds there. Okay. How are they vibrating? The modes of vibration. Try to recollect, in my CO2 laser description, I had given you some description of the vibrational modes of carbon dioxide. Carbon dioxide is a very simple molecule. So, carbon and 2 oxygen. Okay. But in this case, there are much more number of bonds. So, something similar to that. So, there will be lots of methods of vibration. Between C and H, the bonds can vibrate in some way. Between H and N, the bonds can vibrate in some other way. Okay. And those vibrational levels gives rise to these purple states here. Okay. And they are all closely spaced. So, they do not take up much energy. Just give them a little bit of energy and those bonds will start vibrating. Okay. So, that is why these gaps between this energy is very low. So, the gaps between vibrational levels is very low, and the gap between electronic levels, which are shown in red, are large. Okay. So, it is not so easy to say excite the electronic levels, okay, as it is to excite, say, a vibrational level. But these don't limit themselves to only vibrational levels. There are also rotational levels. So, these bonds can rotate, these molecules can rotate in some way. Each of those atoms can rotate with respect to each other in some way. So, those gives rise to also the rotational levels, and I have not shown them separately. They are all there, overlapping levels, which are all there in the purple lines that I have shown. Okay. So, you have a whole bunch of these roto-vibrational levels for each of these electronic states. Okay. So, you have these electronic states and you have these roto-vibrational levels, which is true in the singlet state and also in the triplet state. Okay. So, now what you need is, in order to have a laser, okay, before I go into the laser, I must tell you what is the, for rhodamine 6G, what is the absorption structure and what is the emission structure. So, most of these emission lines are due to the dye, but the dye molecule which I have shown here, okay, the dye molecule is not just the dye molecule, plain dye molecule, it is actually dissolved in some solvents. Okay. It is dissolved in some kind of solvent, and you choose a solvent in such a way that the dye mixes very nicely or very smoothly in those solvents. These dyes are not very different from the dyes which are used, say, in clothes to dye it into a different color, or maybe some dyes which are used in your highlighter pen or colored pens. They are all in the similar category. Okay. So, now these are all in the solvent. Okay. Once they are in the solvent, That means the dye molecules are colliding rampantly with all these solvent molecules also. Okay. So, the dye emission, which may be the fluorescent emission or the lasing emission, whatever. I am talking about the fluorescent emission for the moment. So, all these emissions from the dye, they are all homogeneously broadened. Okay. It is because of the collisional broadening. The collisional broadening gives rise to the homogeneous broadening in the dye. Okay. So, this broadening is a homogeneous one of the emission spectra is what allows the tuning output of the wavelengths. Okay. The tuning output, because see, this reddish part is the emission and this part is the absorption. Okay. So, the dye is absorbing in this 450 nanometer to around 500 nanometer, it will absorb in the 550 nanometer, that the whole thing will be absorbed. So, when it absorbs, actually the excitation of the dye goes from here to this level, or it can also go from this level to this level, depending on the wavelength. Okay. It has to be just more than this. Okay. The wavelength has to be more than this and it will get excited there. And these can get excited to all these roto-vibrational levels, and they relax back into, say, almost the roto-vibrational levels which are in the lowermost state as far as the S1 state is concerned, lowermost of the electronic level. Okay. And even from here it will tumble down into these rotations. From these rotational levels also they will tumble down here. Okay. So, I have the excitation from here to here, okay, and then they tumble down here, non-radiative of course, and then you get this emission. These are the ones which are the emission lines where you get the light. And there are so many rotational levels here and there are so many rotational levels here, So, from one rotational level to the next and the next, some other rotational level to the next, and so it goes on. So, you have whole lot of wavelengths. You just see the length of these lines, they are not all the same, very closely spaced, almost similar line structure, but still they are not the same, they are different. And that itself gives you a wide spectral range. Okay. And on top of that, the collisional broadening, which gives you a spectral range like this. Okay. So, if I talk about this spectral range, you see there is a bit of an overlap. Does not matter, it can overlap. But if you see this line, this is what I want to make use of in my laser, this emission line. Okay. We will talk about more about this part of the spectrum.